Welcome friends. In this session, we describe the notion of groups. We begin with binary operation on a set. A set is a well-defined collection of objects. In this chapter, we discuss binary operation that associates any two elements of a given set to an element in the same set. Binary operations. Definition. Binary operation or binary composition. A binary operation or binary composition on a non-empty set S is a function usually denoted by star, which associate each ordered pair AB of elements A, B in S to a unique element C in S. Usually C is denoted by A star B. Thus, a binary operation star on S is a function such that star is from S cross S to S, where star AB is equal to A star B. If star is a binary operation on a set S, then S is closed under the operation star. Remark. Let G be a non-empty set. By saying G is closed under the binary operation star, it means that for AB in G, A star B belongs to G. Equation number 1. 1 is often known as closure property. Attention. While defining a binary operation star on a set S, the following must always hold. 1. Exactly one element is assigned to each possible ordered pair of elements of S. This property is usually called the binary operation is well defined. 2. For each ordered pair of elements of S, the element assigned to it is again in S. This property is usually called the binary operation is defined everywhere. Example 1. In R, the set of real numbers, addition, subtraction and multiplication are binary compositions, but division is not a binary composition, as 1 belong to R, 0 belong to R, but 1 by 0 is not an element of R. Example 2. Let f be the set of all real valued functions with domain R. Verify whether star defined by f star g is equal to h, where h is a function greater than both f and g is a binary operation or not. Solution. The definition is completely worthless as we have not defined what it means for one function to be greater than another. Even if we had, any sensible definition would result in there being many functions greater than both f and g, and star would still be not well defined. Groups. A group is a set with a binary operation that holds some properties. Precise definition follows. Definition. Group. A group G star is a non-empty set G closed under the binary operation star such that the following axioms are satisfied. G1. Associativity. The binary operation star is associative, that is, A star B star C is equal to A star B star C for every A, B, C in G. G2. Existence of identity. There is an element E in G such that E star A is equal to A star E is equal to A for every A in G. E is called the identity element for star on G. G3. Existence of inverse. For each A in G, there is an element A inverse in G such that A inverse star A is equal to A star A inverse is equal to E. A inverse is called the inverse of A with respect to the operation star. Definition. Abelian group. A group G star is said to be abelian or commutative if the following axiom also holds. G4. Commutativity. A star B is equal to B star A for every AB belongs to G. Finite and infinite groups. If the underlying set G of a group G star consists of finite number of elements, then the group is a finite group. The number of elements in a finite group is called the order of the group. A group that is not a finite group is an infinite group. An infinite group is said to be of infinite order. Notation. The order of a group G is denoted by either one of the following symbols. Example 3. A group with usual addition as an operation. Show that set, the set of integers, is a group with respect to the operation of addition of integers. Is it an abelian group? Discuss the order of the group Z. Solution. Here Z is equal to set consisting of etc. minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Since the addition of two integers gives an integer, addition is a binary operation on set. Now, we verify the three axioms for group. G1. If A, B, C belongs to Z, then A plus B plus C is equal to A plus B plus C. Hence, the associative law is satisfied. G2. There is a number 0 in set such that 0 plus A is equal to A plus 0 for every A in set. Hence, 0 is the identity element in set under the operation addition. G3. If A belongs to set, then there exists minus A in set such that minus A plus A is equal to 0 is equal to A plus minus A. Thus, for every integer, there exists an additive inverse in set. Hence, Z is a group under addition. Moreover, G4 commutative. A plus B is equal to B plus A for every AB in set. Hence, Z is an abelian group. Since the set Z contain infinite number of elements, Z is an infinite group. Hence, Z is a group of infinite order. Similarly, it can be seen that Q, R and C under the operation plus are abelian groups of infinite order. Example 4. A group with usual multiplication as an operation. Show that the set Q star is equal to Q minus set 0 of all non-zero rational numbers forms a group under multiplication. Solution. Since the product of two non-zero rational numbers is also a non-zero rational number, multiplication is an operation on Q star. G1. If A, B, C belongs to Q star, then A into B into C is equal to A into B into C. Hence, the associative law is satisfied. G2. The number 1 belongs to Q star such that 1 into A is equal to A into 1 for every A in Q star. Therefore, 1 is the identity element in Q star for the operation multiplication. G3. If A is equal to P by Q belongs to Q star, then 1 by A is equal to Q by P belongs to Q star such that A into 1 by A is equal to 1 by A into A. Thus, for every non-zero rational number, there exists a multiplicative inverse in Q star. Therefore, Q star is a group under multiplication. G4. Commutativity. Q star is an abelian group as A into B is equal to B into A for every A, B in Q star. Since the underlying set contain infinite number of elements, Q star is an infinite group. Hence, Q star is of infinite order. In a similar way, it can be seen that R star is equal to R minus set 0 and C star is equal to C minus set 0 are abelian groups of infinite order under the operation multiplication. Remark. The set Q of all rational numbers is not a group with respect to multiplication. For corresponding to 0 in Q, there is no rational number A in Q such that 0 into A is equal to 1, the identity element. By the same argument, R and C are not groups with respect to the operation multiplication. Example 5. Examples of set with binary operations that do not give groups. The set n of natural numbers with operation plus is not a group as there is no identity element for plus in n. The set of all non-negative integers with operation plus is still not a group. There is an identity element 0, but 1 has no additive inverse. The set n with the operation multiplication is not a group. There is an identity 1, but 2 has no inverse in n under multiplication. Before proceeding, we recall the following concepts. And square metric A is invertible if its inverse A inverse equal to 1 by determinant of A into adjoint of A exists. A square metric A is singular if determinant of A is equal to 0. If determinant of A not equal to 0, then the metric A is non-singular. A square metric A is invertible if and only if it is non-singular, that is, A is invertible if and only if determinant of A not equal to 0. If A is an invertible square metric of order n, then A inverse is equal to In is equal to A inverse A, where In is n by n identity matrix. Example 6. The set m by n of R of all m by n matrices with operation metric addition is an abelian group of infinite order. The m by n metric with all entries 0 is the identity metric. The set MNR of all n by n metrics with operation metric multiplication is not a group. For the 0 n by n metric with all entries 0 has no multiplicative inverse. Show that the subset S of M and R consists of all n by n invertible matrices, that is matrices with the determinant not equal to 0 with operation metric multiplication is a group. Show that the subset T of M and R consisting of all n by n matrices with the determinant equal to 1 is a group under metric multiplication. The group S seen in 3 above is so important that we call it general linear group of n by n matrices over R and is denoted by GLNR. Also the group in 4 is called special linear group of n by n matrices over R and is denoted by SLNR. Solution to example 6. We discuss 3 in detail, leaving the rest to the exercise. We denote the inverse matrix of A by A inverse. Closure property. Let A, B belongs to S. Then A and B are invertible matrices of order n and A inverse and B inverse exist and is in S, and also A inverse is equal to B inverse is equal to In, where In is the n by n identity matrix. Then AB into B inverse A inverse is equal to A into B inverse into A inverse is equal to A inverse is equal to A inverse, which is equal to In. So that AB is invertible and consequently AB belong to S, showing that metric multiplication is an operation on S. G1. Metric multiplication is associative. G2. In acts as the identity element. G3. By the definition of S, every element in S is invertible and the inverse also belong to S. That is, for every A in S, A inverse belong to S. Also, A inverse is equal to In is equal to A inverse for every A in S. Hence, S is a group with respect to metric multiplication. But the group S is not abelian as metric multiplication is not commutative. Example 7. Show that the set G of multiples of integers by a fixed integer m is a group with respect to usual addition. Solution. Let m be a fixed integer, then the given set is given by G is equal to set consisting of etc. minus 3m, minus 2m, minus m, 0, m, 2m, 3m, etc. We have to show that G plus is a group. Closure property. Let AB belongs to G, then there exist integers R and S such that A is equal to Rm and B is equal to Sm, so that A plus B is equal to Rm plus Sm is equal to R plus Sm, a multiple of m by an integer, and hence A plus B belongs to G. G1. If C is equal to Tm, then A plus B plus C is equal to Rm plus Sm plus Tm, which is equal to R plus S plus T m, which is equal to R plus S plus T m is equal to Rm plus Sm plus Tm is equal to A plus B plus C, showing the associativity. G2. Since 0 is equal to 0 into m, 0 belongs to G and 0 plus A is equal to A is equal to A plus 0 for every A in G. Therefore, 0 is the identity. G3. Let A belongs to G, then A is equal to Rm for some integer R. Now, minus A is equal to minus R into m is also a multiple of m, so that minus A belongs to G, and also A plus minus A is equal to 0 is equal to minus A plus A, showing that inverse of A belongs to G is minus A and is in G. Hence, G is a group with respect to addition. Also, G is an abelian group of infinite order. Example 8. Show that the set G of integral powers of a fixed integer m is a group with respect to usual multiplication. Discuss the order of the group. Solution. Let m be a fixed integer, then G is equal to set consisting of etc. m raised to minus 3, m raised to minus 2, m raised to minus 1, 1 is equal to m raised to 0, m, m square, m cube, etc. We have to show that G is a group with respect to usual multiplication. Closure property. Let AB belongs to G, then there exists integer r and s such that a is equal to m raised to r and b is equal to m raised to s, so that ab is equal to m raised to r, m raised to s is equal to m raised to r plus s, equation number 1. Since r plus s is an integer, one shows that ab is also an integral power of m. Hence, ab belongs to G, showing the G is closed under multiplication. G1. If we also take C is equal to m raised to t, then ab into C is equal to m raised to r, m raised to s into m raised to t is equal to m raised to r plus s, m raised to t is equal to m raised to r plus s plus t, which is equal to m raised to r plus s plus t, which is equal to m raised to r into m raised to s, m raised to t, which is equal to a into bc, showing the associativity. G2. The identity element is 1 is equal to m raised to 0 belongs to G. G3. Let a belongs to G, then a is equal to m raised to r for some integer r. Now, a raised to minus 1 is equal to m raised to minus r is also an integral power of m, so that a inverse belongs to G, and also a into a inverse is equal to 1 is equal to a inverse a, showing that a inverse is the inverse of a. Hence, G is a group with respect to usual multiplication. G4. AB is equal to m raised to r into m raised to s, which is equal to m raised to r plus s is equal to m raised to s plus r, which is equal to m raised to s into m raised to r is equal to BA. Hence, multiplication is commutative and hence G is abelian. Also, since the set G consists of infinite number of elements, G is an infinite abelian group. Example 9. Show that the set Q plus of all positive rational numbers forms an abelian group under the operation defined by A star B is equal to AB by 2. Solution. Note that Q plus is equal to the set consisting of P by Q such that P greater than 0, Q greater than 0 and GCD of PQ is equal to 1. Closure property. Let AB belongs to Q plus. Then A star B is equal to AB by 2 belongs to Q plus, showing that Q plus is closed under the operation star. G1. Let A, B, C belong to Q plus. Then A star B star C is equal to AB by 2 star C is equal to AB by 2 into C by 2, which is equal to ABC by 4, equation number 1. A star B star C is equal to A star BC by 2, which is equal to A into BC by 2 by 2, which is equal to ABC by 4, equation number 2. RHS of 1 and 2 are the same and hence we have A star B star C is equal to A star B star C for every A, B, C in Q plus. G2. If E is the identity element in Q plus with respect to the operation star, we must have A star E is equal to A is equal to E star A for every A in Q plus. Now, A star E is equal to A implies AE by 2 is equal to A implies AE is equal to 2A, which implies A into E minus 2 is equal to 0, which implies E minus 2 is equal to 0, since A not equal to 0 as A belongs to Q plus, which implies E is equal to 2, implies 2 is the identity element and belongs to Q plus. G3. Let A belongs to Q plus. If B is the inverse of A in Q plus with respect to the operation star, then we must have A star B is equal to 2 is equal to B star A. But A star B is equal to 2 implies AB by 2 is equal to 2, which implies AB is equal to 4, which implies B is equal to 4 by A. A belongs to Q plus implies 4 by A belongs to Q plus. Therefore, the inverse of A is 4 by A, an element in Q plus. G4. Commutativity. A star B is equal to AB by 2, which is equal to BA by 2 is equal to B star A for every AB in Q plus. Hence, Q plus is an abelian group under star. Example 10. Show that U is equal to the set consisting of set belongs to C such that mod set is equal to 1 is a group under usual multiplication. Solution is left to the assignments. In this session, we have described the notion of a group, beginning our discussion with binary operation on a set. We have also considered various types of examples to understand the concept. In the next session, we shall discuss elementary properties of groups. Before going to the next session, let us try to answer these questions. 1. Prove that the set C star of all non-zero complex numbers is an abelian group of infinite order with respect to multiplication of complex numbers. 2. Rn denote the set of all n tuples with real entries, that is, Rn is the set of all n component row vectors with real entries. Show that Rn is a group under component-wise addition. A statement or proposition is a sentence which is either true or false but not both. Let S be the set of all statements. Verify that disjunction and conjunction are two binary operations on S. 4. Verify that in N the set of natural numbers LCM, the least common multiple, is a binary operation. Here there are some books for your reference. Ian Herstein, Topics in Algebra, Wiley Eastern Limited, New Delhi, 1975. Nathan Jacobson, Basic Algebra, Volume 1, Hindustan Publishing Corporation, India, Delhi, 1993. John B. Fraley, A First Course in Abstract Algebra, 5th edition, Edison Wesley, California, 1999. Vijay K. Khanna, S. K. Bambri, A Course in Abstract Algebra, Vikas Publishing House Private Limited, New Delhi, 1996. Hope you enjoyed this session. See you next time. Till then, goodbye.